Okay, welcome back to part 2 of the tile editor video, series. This is really probably going to be the only other one, as I'm pretty much done with the core stuff in it. I'll go over the various parts here. Some of the code, mostly the code having to do with shifting the bits left and right. That's kind of a little more of an involved thing. That discussion, by the way, we'll delve a little bit into kind of how the Apple does the graphics and how the data is stored in a given byte, because you have a couple considerations there about how to move things if you're going to shift things by 1 pixel left or right, in the case of the tiles, but within a byte. So right now, and I may end up making a third version, but right now we got Tile Edit 2. This is just a very basic stub. Oops, let me get it over here. And I got a few other things to do to change that I haven't changed yet that I'll talk about, but this is just a very basic stub based on the previous one that I did, where we just set up a framework here. Basically what this does is this just essentially sets up and loads a tile set that you want to load, although it's not really set up generically like that. It's just, right now it just loads the Ultima 4 tile set off the disk. You'll need to modify this if you want to use it for any particular other thing. This particular basic program is not by any means complete, has no error checking of any kind, is not generically made to work with, any tile set or one you make. It's literally just, at the moment, hard-coded in for Ultima 4 tiles. You could change any of that, of course, and you'll want to, and either add in the ability to flip between all of the sets. My idea was to maybe make a custom option, so if you're working on your own game and you want to go back and forth in some meaningful way, or just make it so that down here at the bottom there was going to be like a menu that would just do like you'd go load, a tile set, and it would be like number 1 would be Ultima 3, number 2 would be Ultima 4, and so on and so forth. Number 3 would be Ultima 5 Part 1, the half of the set, and then the other 4 would be the other half, or whatever. And then maybe a custom, like a one off the end there, that'd be whatever your custom set is or something like that. Again, this does not have features. This is just the framework, just this kind of stuff. Essentially, this Poke 769. Right now, this is what you use to tell it which tile. I was going to have it originally where you come back out to basic to change the tile, because it's easier to deal with typing in numbers and titles and names, and typing things in here in basic than it is in machine language. But it runs fast enough that for now you can, when you're in the tile editor, you can just plus and minus through the set, and it's pretty fast to do that. So it's not too cumbersome to go back and forth sequentially from tile to tile to get the one you want. But you can put that in. If you do put that in, when you call the routine, which is right here, this is the current address. This is what you'd have to change if you modify the program, of course. But currently, this call takes us into the machine language editor. This tells it which tile number to use. You can skip the U4 stuff, because I was going to make that as like an automatic switch. This is latent from the previous program. To switch between Ultima 4 and Ultima 5. You can use it if you want. I'm not using it right now. I just left it in there because I thought I was going to use it. I put the cursor at like 1 down 4, like up here somewhere underneath the graphics screen, so that it doesn't sit down here when it's waiting for a key press, basically. You could, again, modify that as you see fit. And we'll get into how to run the program here in a second. Let me show you a little bit more of the code. So that's the main loop up there. Then basically up there, it just loops around waiting for a key press. Here we load our files. Again, this is the tile edit assembler program into 6000. And again, you modify these as you see fit. But the tiles get loaded into 4000. And I set up a separate one for 4 and 5. Like the basic 256 of 5, because in most cases, well, I guess you could work on either one if you were to really work on those tiles. And then I created something here that I haven't implemented yet for creating a file name. I don't think you can use fn because it treats it as a function of some kind or some other thing. So I did tname, and I gave them names with a return so that, to make it easier to load them. Again, I was thinking of doing the autoloader where you just use 1, 2, 3, 4, 5 or whatever. Then down here, we've got some stuff that I've added to the machine language program. To be some simple calls from basic to clear the text. This clears the bottom 4 lines of text to spaces, blank. This puts up the basic menu, And this, I believe, is that the call itself? I think that's the call itself to go into the editor, which really is kind of redundant, but I was planning on making these more callable. Right now, it just does it here. Oh, no, it does. Right here, 9 to 5. There you go. No, I take that back. Go sub, call. Go to 1,000, go sub 9,000. Go sub 9,005. Oh, yeah, and then, oh, it is there. It is here. It's in the command loop. Sorry, my fault. Did stuff so recently I forgot. Here we go. When we hit E, then we call 9010 to go into the machine language. So the way this is basically designed to work is, since it's easier in BASIC to handle file names, loading files, saving files, I figured we would do all that stuff in BASIC. So you're going to actually use a kind of a mode switch. You use the E key, and I'll run that here real quick and show you. So you'll get this menu, and this is, again, a machine language call to kind of print that menu. It's in the machine language. It's in the code over here in the main machine language. There's a call and a jump to get here, a jump table, basically. And then so you can see here you're in file. This is the mode. This is the mode you're in, file edit. And it could be named whatever, but I was going to do other stuff with it, but files are really what we're mainly after here. You can load and save, which don't do anything right now. There's no command here. But E says edit tile. If you hit E, it switches to the tile edit mode. So now you're in tile edit, and it says exit edit. And this is all the stuff you can do. I put in various things in inverse here to show you what the basic commands are. We'll go over them a little bit too. They are not, let's see, how can I say this? They are not, this is not, like, it doesn't really describe everything. It's just a quick reference. You're supposed to know what to do. So, for instance, arrow move means to move around the screen up here, you use the arrow keys. And the other weird one here is Control WASD, which is shift 1 pixel. That shifts it left, right, up, or down. And you're probably going to say, well, why don't you just use the arrow keys or control something like that? Well, Control IJKM and Control arrow keys versus just plain. For some reason, I don't know if it's this or I just don't know how to do it, but I kept getting like the same key. Like I'd read the key and check the value to see what the control key was versus the regular key. And in some cases, I got the same value. So I couldn't isolate control versus non-control for those keys. So I figured, okay, well, now, maybe not back in the day, but now we know what, WASD means up, down, left, right in gaming. It has for a long time. Probably not back in the day here when this was, out, when this type of stuff was being done, but we do know that now. So it's a familiar construct. So I figured, okay, well, I'll just move it to control. And it also kind of works because now you can control shift with your left hand and use the mouse with your right, or use whatever other, the regular arrow keys with your right or whatever you want, if you want to. So it does get them separated enough so that you don't confuse them. And I also made it a control sequence so you don't accidentally shift things around. Invert will reverse the entire thing. Plus and minus. Now, you don't have to, it's plus and minus on a modern keyboard. I don't know what it's going to show, what it's going to work like on a, I think it's the equal key is what it's really looking for, because on a modern keyboard, it's the minus key is minus, unshifted, but the plus key is equals. So it's really those two keys. So plus, I say plus, is really equal. Maybe I should change that to just the equal sign. It probably would work. But I don't know what that looks like on a Apple keyboard. I have to look it up and see if equal and plus are in, or equal and minus are in places that would help that. But right now on a modern keyboard in the emulator, they're right next to each other, so it's a lot easier to just use those two keys. And you can modify that if you need to. Spacebar changes a pixel, so we can get a pixel change here. And again, I think we talked about before, the palette changes the palette for that byte. Now, again, this is constructed of 7 characters, 7 pixels, and then 7 pixels. This is byte number 1, or the left half of the row, if you will. So there's 32 bytes here, 2 wide, 16 tall. So the leftmost batch here is 7 pixels, and the rightmost ones are 7 pixels. And we'll get into this in a second about the actual pixels, but from a color standpoint, each byte holds 3.5 color pixels, sort of. But from a pure pixel standpoint, each bit is a pixel. So you only get color if they do a certain way. You can see the pattern here. Every other one with this palette is green. and every other one, if you were to do this, is purple. So, and if you do them, any two consecutively is white. So it gets a little, this is very weird, it's very clever the way they did it back then, because it was the first computer to actually do color, and it actually gave you a few colors, which was more than anybody else had ever expected. Even in low res, you got 16 colors, which is way more than anyone expected on that type of thing. But anyway, so it's got its idiosyncrasies, of course, and we'll get into that a little bit. I'm not going to do a full dissertation on Apple graphics, but I do want to give an example and show, kind of how, delve into it a little bit, so it's a starting point. If you haven't ever done it, you'll definitely want to look it up and get into it a little bit more. The whole thing with, like I did in some of the earlier videos about the graphics row, a table for each graphics, each line of the screen, and all that stuff is just a gigantic pain in the neck to work with. But wait, it gets better, because shifting bits is even worse. Because bit 7 is, when we do this palette shift, that sets bit 7. The way they did this was that bit 7, if it's high, if it's low, it's the standard green and purple palette, and if it's high, it gives you blue and orange, which is a decent color scheme. Purple's a little weird, but okay. But you get these primary colors. You get 6 of them, with white and black being doubled. Black, of course, would be 0 anyway, so that's doubled. But 2 pixels in a row is white, regardless of which palette you're on. So there you are. But that bit 7 becomes when you're shifting pixels left and right in any meaningful way. And that's why you'll see in many graphics, many games, there are not too many games that are going to use just a single byte wide character. Some do, but most are going to make them a little larger. So they're going to be like this. They're going to be at least two bytes wide, and then they move across the screen. Well, you have to shift these a certain way, of course, and if you're doing color especially. But even but that's why you probably see only mostly white characters on screen. You look at Sneakers, even Pac-Man, some of those, they just use white, because it's easier to deal with. Because then you just do pixels in a row, and you get white, and that's it. It's easier to, if you shift it, it still stays white. If you're doing color, then you got to deal with shifting it a certain way to keep the color and the palette, which is impossible, because, and we'll see in a little bit, it'd be impossible to shift this one pixel at a time across the screen, or even by colors, and keep the palette settings, because the palette is per byte, so it's only these 7 pixels. Well, then the palette shifts over here to these last 7 pixels. Well, how do you do, if you're on palette, if this, let's just do it this way, if this, which you can see now, that turns red, is one palette, and then this over here is the other palette. Well, if you're moving these bytes to the right across the screen, how do you make that red when it goes over here? You have to track all that and figure out where the byte boundary changes and all that stuff, and that's why you'll see what I did a little differently on mine for this. If somebody wants to do that, to go through that work, you go right ahead. But I found it difficult, not impossible, but it'd be very, very difficult and a lot more code to somehow track that, to see when the byte boundary changed enough to where I don't know I don't even know how you do this, really, how you would do that, because you would end up with just, well, I don't know, it would be very, very difficult, if not impossible, to track that across. That's why if you do that, if you make a game like that, you probably are going to keep the palette the same between the 2 consecutive bytes left to right. You probably wouldn't switch palettes because it's just too much to manage. Then you could move things around in color a little bit easier. You just move them 2 pixels at a time, but you still have the rotational things we're going to talk about, which is a real pain in the neck. The other one is C for cycle tiles. That changes these inner tiles here. This again was like I wanted to paint whatever the tile you're working on, and then I wanted you to be able to cycle through other tiles to see how they look in context to that that tile. So this lets you just cycle. The cycling in this case, it just goes forward. So it just goes, I think it's 15 on the screen at one time, so it just goes, adds 15 to the tile start here and just rips them out sequentially. The plus or minus moves you tile by tile back and forth 1 tile. We did that already. Shifting pixels now. I'm going to show you, and then we're going to go into some of the code. So shifting up and down is easy. You can even preserve the palettes because, well, you're not even touching the palette. Because when you shift up and down, you're just moving entire bytes. You're taking these top 2 bytes, you're putting them at the bottom, you're moving every other byte up by 2 bytes. So you're dealing with a whole byte. So everything is preserved. So if you have a palette switch, for instance, here, and watch this not work, and then you shift it up, it should stay because you haven't touched the bit. You haven't shifted any bits or anything like that. You're just moving the bytes. So that's very handy and works fine. So up, down works great. Left to right, we ran into a problem with, like I said, all the bit twiddling and having the high bit for the palette, and being able to figure out, or even if you wanted to figure out, well, if this is red, how do I know when it goes over here, you know, without tracking every byte or something like that? I don't even know, or the, you know, the palette setting for each byte as you shift it, and from previous shifts, because you have to track it across several shifts. If you're writing a game, you're just moving across to the right. Well, you can probably track that, but in this, you can arbitrarily move up, down, left, right, shifting, and, you know, how do I know, right? So what I did was, and because of the difficulty, as you see in the programming, whenever you do a left or right shift with this, it clears the palette bit to 0 on all bytes, regardless. So if you have palettes, if you're dealing with a mixed palette, you know, like a lot of tiles, like in this particular instance, use the same palette, you know. They don't change them, like, they don't necessarily, they don't do too much of palette here, right? So we're not dealing with too much in the way of palettes and random bytes. But if you do have something like that, where there's some bytes have a palette, different palette, then it's going to be cleared. So it's going to be cleared to green and purple and white. So just be aware of that, that shifting left and right is going to clear the palettes, and you'll have to manually reset your palette for any given bytes that you would want them to have. So I would recommend, if you're using this, and you don't want to write a bunch of code to get around that or figure that out, just, you know, try to do your shifting, you know, as you're constructing your tiles, and shift things around the position you want. Because you could certainly see a case for doing it like here, where we are going to do, you know, you say, oh, this is grass. Well, I want to see how the grass looks, and you may want to move it around because that whole pattern shifts, you know, how they look in context, because it's a repeating tile. And certain positions look better in the repetition than others. Like, that's pretty good. That's not too bad. That's different from the original, but it's not too shabby. So, you know, if you're doing something like this, you want to shift your stuff around and then deal with the palette. Because you may want to go, you know what, I think I want to have this one be kind of a red. I want this one to be a red. And I want this one to be a red to simulate, I don't know, burnt grass or something. But if you were to shift it, they all go back. So just be aware of that. Okay, so now, and then E would just take you back to the basic, and you can flip back and forth from there. That's the basic structure of in the commands and how things work. That's pretty much all I got. Just real basic. You know, you move around, you hit space bar to change the pixel and all that stuff. And but you can edit everything or edit tiles this way. So now, the code here, we're not going to go into all the code. I'm going to go into some of it. It's mostly straightforward. The only thing about it, and I'm probably going to change this, so some of the values in those call statements that you saw in BASIC will change, because I was originally possibly planning to use this to make a map editor, but I realized that that isn't going to really work for this anyway, and I've got a bunch of data in here that is, you know, buffers for maps and blah blah blah. There's some stuff I'd have to keep, like the tile tables and the graphics row table, but there's a bunch of things, like there's 1K of map data here, which we're not going to need. I already took out the map routines. The map get from the disk sector buffer can go. So I got to clean this up a bit first. So those addresses that you saw on screen will change. They'll be documented in here, or you can always pull them off. The big thing about how this works, how this is put together, and how I would recommend doing it this way if you're going to go back and forth with BASIC, unless you want to do everything in machine language, in case, you know, go right ahead and do whatever you need, or whatever you want to do it. We do a, where'd it go? Where's my jump thing? I should have a jump table here. Here we go. Yeah, here we go. So what I did was, this is the entry point. So when you call, it goes here. From BASIC, though, if you go 3 bytes after this, you know, so it's a jump and 2 bytes for the address, you go here, which is to clear the text window. And if you go 4 byte and then return, so it jumps there, clears the text window, returns back to BASIC. These are for BASIC calls. And then you got another table here, or another jump here for setting up the BASIC text menu. And I did that because it was just as easy to do it here as in BASIC, and it takes up less room in BASIC. So I've already got this going anyway, and it's faster. So and then we return. You just put any other tables in here that you want, or tables, jump vectors here, if you want to have stuff back and forth with BASIC. I don't know what other features you could really be adding too much to the tile editor, but, you know, if you want to do that. And from there, I got some stuff I'm going to delete out here for, again, the Ultima 4, Ultima 5 stuff. This doesn't really apply, and it really was about this, which doesn't really matter for this because we're editing the tiles directly. This was if you were to use the other program, the one that we were using to paint the map and paint the tiles on the screen, would replace place a character, the Ultima 5 hero character, in one of the tiles to use. But that's not here, so we're going to take that out. Anyway, so most of this is pretty straightforward from a programming standpoint. You do your directional keys, you get a key, you check it, you go around, and however you want to do this stuff. I just did it the most. Remember, I do things the most straightforward way first and then try to modify if I need to from there. But we don't really have a lot of considerations here as much considerations for memory efficiency and coding efficiency, because we're only manipulating, the most we're ever manipulating is 32 bytes at a time. And even then, like the bit shifting, for instance. And you can see that was reasonably fast. This is on a standard, 1 megahertz, speed thing. And it's pretty much fast enough for doing editing. It's not particularly slow. And it's repainting this screen too if you do like that. So it's all pretty quick. And you could always jack that way up if you need more speed. So I didn't worry too much about efficiency of code, either from a memory standpoint or from a, what's the fastest way possible, unlike the other program where we really wanted to pump out pixels to the screen as fast as humanly possible. So we do the things with the keys here, process our keystrokes. This is left over from the other program where we wanted to have both directionals move you in the direction, but in this case we're doing it differently. Anyway, and then, okay, proceed left, right, up, down. And I went over some of this in the previous program about how it flips the various bits and stuff. Okay, flip bit. Process bit change. Yeah, this is where we flip the bit for whatever pixel you're changing. Show palette colors. This just shows this on screen here. Invert tile is very easy. You just EOR it with 7F and run through the whole 32 bytes and repaint the screens, the stuff on the screen. So now, okay, shift tile up and down again is pretty straightforward. I did this in the same manner, not for speed, just because it was easier to do the indexing, where we do the absolute addressing instead of 0 page, and we just take the tile, the low and the high byte. We actually calculate the tile address of the tile in question, whatever tile we're working on, tile index, right? And we store those in 0 page, which I think is not even used here. Well, yeah, it kind of is. It kind of is. Because we're going to use that to preserve the top or the bottom 2 bytes. Just, again, it's easier. But this one, because the main loop, I went ahead and just put the hard-coded, so all of these addresses get changed to whatever that is. It gets changed to whatever the address is for the tile. So that gets modified in real time. And then we do 32 bytes. And then we put again, top or bottom. This is reversible, so top or bottom. We put the bytes from the top to the bottom or bottom to the top, depending which direction we're moving. So that's those two routines. Again, you could make this a lot more efficient by just, going a different direction and using most of the same code. You could probably put this, well, I don't know, maybe not, but anyway. But shifting left and right. Now this is where it gets sticky. So just to give you a little bit of a picture here of what we're looking at. So this is where we got to get in. Now this is the part that's going to be a little bit of discussion. So if you want to settle in for a minute, it shouldn't take real long, but it's definitely going to take a few minutes to kind of cover this. And this is by no means a dissertation on all of how this works, but this will give you a pretty good idea of how Apple graphics work. All right, so in this case we got 2 bytes next to each other, right? In memory, just how bytes are stored, they are stored this way. So if you're shifting things left to right, the leftmost bit is 7, bit 7, okay? And the rightmost bit is 0. However, when Apple displays it on screen, it goes the opposite direction. It starts at 0 and goes to 6, bit 6. Bit 7, remember, is the palette, does not get displayed. So if you think about that, you've got 7 pixels here. hence where you get the idea of 3.5 color pixels. You got 3 full pairs, 2, 4, 6, and then you got 1 extra bit. And that extra bit comes into play on the next byte. So when it remember, it always spits out these pixels just one right after the other. Color is a function of its the color clock and its position in the bit well, not really the bit pattern, but if there's anything next to it or not. So essentially, if you have 0, 1, you get 2 bits. This is 1, 0. So then there's one that's got a color. It's just a single bit. If they were both 1s, you'd get white. If it's 0, 1, you get probably green. And if it's 1, 0, starts with 1 and goes to 0, then you get a different color. And that's fairly similar. The idea of having 2 bits per color is similar to what will come later. But again, it's done a little bit differently here because you can actually do 3 bits in a row and still get solid white with this system. Which is why you get things like, when you look at some of this stuff, you can get these nice, smooth edges that are high res because this is 1 pixel apart, not 2. It would be much more jagged and it would be a steeper angle. But here, you've got a nice smooth edge that's pure white. You see that some of these aren't even fringing because they're consecutive. You can see a single pixel here. These single pixels are fringing because they're a single pixel. It also does give you the advantage. This is the one big advantage this whole system is, and the only computer that did this without, well, not the only computer that did this, but without eating up a lot more memory or doing things a different way, is that you can actually light up a single pixel as a color. It's paired in order to do that. If you were to put another green next to this, you get a much wider bar. You get something like this. But if you put just one, well, let's look at that actually. So if we got this one here, if we put another one next to it, see how that looks like 3 times wider or 4? But if you do this, you get a very fine single pixel. So by manipulating this, you can get some pretty finely done graphics in certain cases. If you wanted a horizontal, thing like this, you get a much wider pixel. The normal way this would look on most machines would probably be not quite as wide as that. Well, maybe that wide, because that would be your 140 pixels across or 160 pixels across in color. We call them fat pixels in most cases, because they're not a single bit pixel like this. On the Atari, for instance, if you do this, you will get a single pixel as well. It'll just be color artifacted in the same way. It'll just be they just don't have as many colors. It's like blue and red, I think. But you will get the same deal. You'll get if you do 2 of them, you'll get white on the Atari. Depending on how you set your color palette, that actually has color palettes. But for the basic, black background, white foreground color, it's a 2-color mode. Then the artifacting colors are red and blue when you do a single pixel. And so you will get this super fine pixel thing. But back in this time, this is 77 when this came out, that was like, that was not something you would see. Color, let alone the nice fine detail like that. But most systems later on would do color in more of a paired system. So some of them would do the artifacting that existed, so you could still get like 320, actual pixels in color. But most of them did the fat pixels, which would pair them, and you'd actually have any color pixel would be 2 clocks wide, 2 pixels wide. Anyway, that's enough of that. But on the Apple, like I said, you can do 3, or you can do something like this where you get a nice fine edge that's 1 pixel off. Each one of these is 1 pixel off, not 2. Where 2 would be much more like this, probably much wider. Anyway, so that's how it displays. So it displays in reverse order from the way that the pixels go, and then bit 7 is your palette. And we'll get in. I'm not going to get into that, but basically the way the palette thing works, just as a brief thing, is that when you let's see if we can actually simulate this here. I'm not sure how well this emulator will show this. Yeah, it kind of doesn't show it. But what really happens is, so you see this, it's going to change that pixel there. So when I shift the palette, you can see there's just an ever so slight shift in the pixel. It's kind of hard to see on this screen, but the pixel shifts just slightly to one side. Because what they're doing, the trick they're doing, that Steve Wozniak did, was he delayed the clock cycle on one of the palettes by a certain amount of time, a very minuscule amount of time. Well, so if you think of the cycle as like a circle, like 360, it was delayed like 45 degrees or something like that instead of or 180 or something like that, whatever it is, equivalent, idea. But he delayed it a certain amount of time, and that shifted the pixel enough to give it a different color, and that's why you have the colors that way. That's just a little thing. But anyway, so we've got. So that's the palette bit. So when we're shifting things around, this gets weird. So I initially set this up to shift left, which, because it's reversed, would shift right, mind you, on screen. So the shift right, which means we go left in the actual bit shifting, is we bring all the bits to the left. We rotate. We actually do the code where we actually originally I was preserving bit 7. I was just checking to see if it was set, and then setting a variable. That's this temp variable, to say, okay, the palette bit is set. Actually, I did up here. But I decided I was going to track that because of the stuff I described before, because there's no way to know where that bit would come into play as you keep shifting left or right. So eventually I just cleared this. So what we're doing now is we're clearing bit 7 entirely. So as soon as we start working on these bytes, we clear bit 7. Then we shift, which puts bit 6 into bit 7, and 0 goes into the front. So, okay. So then what we have to do is, but bit 6, because bit 6 has gone into bit 7, and bit 7 is not displayed, it's the palette bit, we now have to move that. We take whatever that value is, and we move it to bit 0, to go around, to wrap around. Because if you do this enough, you'll just wrap around. So we take bit 6, we put it into 0, we take this bit 6, put it back over here into 0. Now again, conceptually this is very easy to describe. You say, oh yeah, just do that. It's not as easy to figure out the math on this. And I'm not a genius at this stuff, at manipulating things like this. I got it to work, but it took a couple hours to kind of work out how to do it. Because again, your considerations are, when this displays, you need to have these consecutive. And then of course you go the opposite direction essentially when you do the other way. But by clearing bit 7 and not dealing with it, then we could say, okay, well, bit 6 could be on or off, right? So when it gets rotated into bit 7, since that's the high bit, an easy way to do that is to just say, is the value of the byte now over 128? If it is, the high bit is set. And then, because we know we cleared it, we can then say, okay, so if it's set, we know it's going to be let's see, how do we do this now? I just realized I didn't know how I did this. I may have forgotten how I did this, because that would be the palette bit. Maybe I should check my code. I'm not sure how I did that. Not because I'm thinking about it. I'm like, that shouldn't work the way I had in mind. Which was to say, because then you'd have to re-clear it. You'd have to move it over here and re-clear that bit. Oh, it doesn't. Well, it does matter though, because we want to clear it. I think I checked it. I put it into a separate variable, and then I put it over, and then I took that variable and added it. So anyway, this is, like I said, yeah, I'm confused. I had to go through this like 3 or 4 times with different ways of doing it. I may have even confused myself now. All right. So what we do is we definitely set our bit 6 thing to, this is going, this is going right. This is the one that I did a little bit. I did the right, going right first, and I did left, and I modified. This is where I changed it to the way I'm describing now. So I'm kind of getting confused between the two methods. And I haven't really modified the other one except to just rem out statements that didn't apply to make it work the same way. This is not true. We clear temp 3 and 4, which are going to be the bit representing bit 6. Remember, the palette bits, if we were to deal them, would have been dealt with separately. Then we get we're on the first byte, so we're on the left-hand byte over here. And we clear bit 7 there. So we clear up bit 7. So that's 0 now. Then we shift right, because what we need to make sure of here is that when we shift right, if this was set, now bit 6 would be set. And we don't want bit 6 to be set. Well, it doesn't really matter. We're going to replace it anyway. But there's a reason to have it be 0. If it's 0, that's what I was going to do. If it's 0, we can then, because we know it's 0, because we clear bit 7, we rotate right. We know bit 6 is now 0. So we can now check, we'll be checking our setting for the bits when we get the bits together, and to have verified whether bits, well, actually bit 0 in this case, was set, because we're going this way. So ignore this chart, we're going the other way. And so when we check 0, which goes out into the carry, and we check the carry, if that is set, that means that bit was set. So that, since that has to go into bit 6, remember 0 goes to 6 in this instance, not the other way around here. So this would go this way. Then we know 6 and 7 are 0. So all we have to do is just add 64 to very simply flip bit 6, essentially. So that became a very easy way to deal with this. You kind of do it the same way, going the opposite way, but there's a little bit different. But it's a similar method where you use the carry as the thing gets rotated out. The trouble is going the other way. Bit 7 goes out, and we don't care about bit 7. So you have to actually check bit 6 differently first, and then do the thing. Actually, I don't think you have to do anything with that. Yeah, you do. You have to go over there and then check it, and then rotate it over there in a similar fashion. So if you're going the other way, bit 6 goes into 7, but 7 doesn't get displayed. It's not a valid. That needs to go over to 0. So whatever this is, when we shift it, we can just check high bit. We say, is it greater than 128? If it is, or equal to 128, because it could be zeros, then we know that this bit is set, and then we just add 1 over here. Because once we shift, like I said, this gets very complicated. So when you shift, 0 comes in, and the whatever end goes out. Now, this particular routine I'm talking about initially here is going this way, but for the moment I'm going to switch to going this way, just because of the differences. So going left, shifting the opposite way, like I said, 6 would go into here, 7 goes into the carry, which we don't care about because we're discarding it anyway, but 6 goes into here, and we don't want 6 to be, if it is set, we need to check it and store it. So we store it into temp 4, but we clear the bit, we clear that bit 7 because we don't want it to be affecting the palette. And then we would use temp 4 to go and put into this over here. Really, I think we just do an add, because either it's 0 or 1. So we just set it accordingly. We just check it and set it, and and then we just add it, because since we're adding to the beginning, bit 0 is 1 or 0. So you can just use an add, just math. Going the other way, like I said, it's a little bit different consideration, like I just described a minute ago, because you know, of how bit 6 and 7, you clear bit 6 and 7, or you clear bit 7, then bit 6 becomes that. This is going this way now. So instead of shifting to the left, we're now shifting to the right, which is this routine here. Now, mind you, it says shift left, but to shift the bits, you got to shift the bits right, because it displays in the opposite direction on the display. Like I said, this gets really complicated. Even I'm not describing it all that greatly. I understand it now, but it's all very counterintuitive. Just think opposite in every single way, basically. But anyway, so when we're going that way and we're going right, then we clear bit 7, we shift it right, and the 0 goes out into the carry. We check the carry, and we set temp according to that. Temp is already 0, so we only really have to say, is the carry set? If the carry is set, we set temp 3 to 1, or whichever one it is, because we've already cleared, we've already cleared these temp variables to 0. And then, since we're going again opposite of this diagram, we then add temp 3 to bit 0 from here that we checked the carry on, and we set maybe it's temp 4. We set temp 4 to 1 or 0. You know, it starts at 0. If the carry that got rotated out was in bit 0, then we set temp 4 to 1, and then we just add it to the next thing over here. And we do the same thing with this one. When that goes to the carry, we adjust temp 3 accordingly, and that goes into bit 6. And because we've cleared bit 7, when we rotate right, bit 6 is now clear as well. And 0 comes into, when you do the rotations, 0 comes in. It doesn't care. It's not a rotation like where you take the bit off the end and rotate it in, or the carry. Maybe it is the carry, but you clear the carry if that's the case. I think it puts just 0. I don't think it even puts the carry in it. This is not the one that does the carry. So we got 0 in bits 6 and 7, and then instead of just adding it, we check, because we're going that way, and we have to now move the bits from here into the higher bits, we check to see if our variable is set. If it is, we add 64. So if the carry from over here was set, if this had a bit and got rotated in the carry, and we set this to 1, we check if it's 1, and then we turn that on by adding 64. So that's essentially what's going on here. This is the 64 add. We clear bit 7, we rotate, we store it, we check it for the carry. We skip over this if it's 0, if the carry is clear because there was no bit, and temp 7 or the temp 4 is already 0. But if it's not, we need to add 64. Do that twice for both bytes, and then we basically just do a standard add. We just add them together. Because actually I should take this back. We actually made that 64. So this either has these temp ones as 0, which means nothing was rotated out of the byte, or we set it to 64, which is essentially the bit we need. And because bit 6 and 7 are 0, we don't really have to check if it's greater than 64 or whatever, because we already know it's going to be less than 64 by definition, because we cleared both top bits. Again, this is what I came up with. There may be better ways to do this, I don't know, but this is the way that actually works for me. And then we just do a standard looping thing. And like I said, going the other way, and there's some palette stuff in here where we're not doing, because again, we cleared the palette. I did a similar kind of thing where I just basically said, except this we have to compare because we have to get around which direction that's going and how that would affect things, because you could end up going the other way here. This is the original, the way the diagram actually goes. Bit 6 could be set, and you could end up with that one bit going into bit 7, which we've already cleared. Actually, I guess we don't have to clear that. So we have to check that a different way, because we can't, because of the way it shifts. We could end up, in other words, we could end up shifting a value into. We could end up shifting a value into the high bit, and we don't want that. So merely clearing the high bit won't work because we're going in that direction. Going the other way, it's easier that way. So we do that, check it. In this case, we just say, and then in this case, because we're coming the other direction, if bit 6, which is now in bit 7, is 1, we're not doing the carry thing because we're not going that direction. Because if we were doing it the regular, if all bits were used, we could use the same thing both ways. 7 would go out into the carry, and then we could check it that way. But 7 is a special case, bit 7, so we can't because of the palette. So we have to actually check this. And then, because that's coming around to the first part of the byte, in whichever direction you're going, or whichever byte you're going to, we know that this 0, or that bit 0, has a value of 1 if you wanted to set it. So we just make it 1 if it needs to be set. If it doesn't, because, again, when you shift these, a 0 goes in, and the other end of it goes into the carry. So a 0 comes in, so we know that bit 0 is 0 each time we shift it. So we only need to know if we need to set it to 1 or not. And we basically make those, not adjustments, we basically figure that out, and then we do the same thing, we do our math to add, essentially add to the front end, and then we clear bit 7 after, because we needed, well, we didn't really need to check it, but we could have done it up there. But we clear bit 7 at the end in this case. And then we store everything back into the original thing, the original byte. And this was palette stuff. Again, this stuff we're not doing. This was my attempt to shift the palette bytes around as well, but then I realized that was kind of fruitless because it wasn't going to do anything that would give you any real use. It took a lot of messing around, and it still didn't work entirely anyway. I had a weird situation where I could shift the entire tile. For instance, I could shift the entire tile like this, right? Now watch this byte. So this byte here, or this bit, when it came around to getting close to that boundary, when it crossed the boundary, but only when this byte's palette was set, and when it hit here, it would now leave a trail behind of bits. It would set a bit every single way, so you'd have a line going across that would form. And I kind of think I knew what happened, but it was like, okay, this is getting to be kind of just a gigantic pain in the neck. And that's when I realized, well, wait, even if I did that, how on earth would I know when this palette bit, which affects, let's say, this pixel here. Let's say we're here. How on earth am I going to know that this bit has now moved into this byte? How am I going to track that? I mean, I suppose you could track consecutive moves to the right, and if you do 7 of them, you say, oh, okay, let's move the palette bit, but I just thought that was going to be just too much of a nightmare. So I just took out the palette bit stuff entirely for left and right moves. Anyway, that's probably the hardest bit in all of this. Everything else is pretty straightforward. Inverting is, as I said, is pretty easy. Drawing the tile block and all that stuff is what you think it is. You just call the tile draw routine and do a loop and give it an XY coordinate. I set up the tile draw one. I modified the tile drawing routine from the previous program to draw arbitrarily to anywhere on the screen with an XY coordinate, with the exception of this border up here. Don't know why I did it that way. I didn't really have to, I suppose, but I just left it in, you know, kind of a thing from before. You could draw over here if you want to as well, but I wanted to be able to get this space filled, so I just made it so that you can address this area by an X and Y coordinate called X tile and Y tile. So you can actually just draw those tiles fairly arbitrarily that way and do a standard, you know, X by Y loop. And that's, I think, pretty much it. I think I went through most of this stuff before, where we set and clear pixels, which is on the screen, and paint the tile pixels and paint the cursor and all that kind of stuff. If not, if you've ever done any editing, written any editing programs like this, it's pretty straightforward stuff. This stuff is. So there's nothing really to tell here. There's nothing all that great. Once again, I did the I did the text in the stupidest, most straightforward way possible of just, you know, hard addresses and increment a counter and just letter at a time. So I just laid out all this text stuff down here, and then, you know, and again, it was just faster to do. I could have done a thing where we put the text in, put a delimiter in for the text, write the code to loop it, give an XY coordinate on the within the window and a memory address, but the memory there, as I mentioned before, is not. These rows are not consecutive, so they are also split up like, and there's a gap, there's skips in the memory like the main screen has. So we're just like, well, that's not going to help very much for trying to code this all up. Like, you can do it, but you know, come up with all this stuff, figure out where everything goes, figure out where each of these goes. And it was just like, you know, by the time I do all that, memory-wise, it's going to be a little bit shorter, but not a heck of a lot. Still need the text either way. And this way, it was just, you know, I could just whip it out. So it's the stupidest, most straightforward way possible, but oh well. So that's pretty much about it for the program. Once I get these, once I figure out how to set up the disks the way I want, so that I have the stuff separated enough, what will need to happen is, so this is my work disk now, but when I put this out, all of the tile sets, like these U5 tiles and U4 tiles, U3, those are all going to be on a separate disk by themselves. I'm going to separate them and just put the programs on one disk and all the finished tile sets on another, and then I'll have another disk that is going to have the source files to make the sets, as well with the sets. So you could, if you really wanted to, you can mess with that. From the original screen captures, they were like a screen capture, or like a B save. You know, they were tiles were laid on the screen, then there was a B save into a graphics file, into just a binary, so that you would load into graphics page 1 or whatever. So I'm going to separate all this stuff out. That way, if anybody complains about the tiles being provided and they get taken down, or they get requested to be taken down, the code stuff will still be here to be able to make everything, if you can find all the sources and stuff like that, and match up the file names the way I've created them and stuff like that. Not hard to do, not terribly hard to do. And excuse me. But that way, at least all of the code for this stuff, and ultimately this, which I'll have to put together into a separate file because this is, you know, Windows based or whatever. I'll make that available somewhere, probably Apple Fritter website, maybe Atari Age, maybe both. I'm not sure. And we'll see what if anybody wants to, you know, use them for anything. But that way the stuff will be kind of available. Just not sure when. I got to sit down and figure this out and separate everything and get it to where I want it, and then kind of inquire as to where the best place would be. If you got any ideas about that, please leave it in the comments. But those are the two sites I'm thinking of. I don't know if there's a more standard or whatever repository for stuff like this, code like this, when people do things in disks. But that's how we're going to break it down to get things set up so that have the best chance of. So what will happen is, so what you'll need to do to use these programs is you'll need to either make or get, if the disk is available that has the tile sets, you're going to need to copy them over to this disk with all of the make programs. So that's one thing. And or make your own, tile set and put them on here, since this disk will not have them. So just be aware of that when you grab the disk. You go, hey, it's not working. The tiles aren't there. But it's because they're not going to be there. You have to use copy to PC or some other thing to move the files over onto this disk to use these. All right, that's about it. Thank you for watching. Hope you get something out of this, and hope somebody is able to use these to make something interesting and fun, or at least learn. And it was quite an experience. I always wanted to mess around with this stuff. I wasn't really planning on making an editor as such, but I thought why not? Had some ideas about it, and at least it'll get a head start on making a very small set of tools to mess around with this kind of stuff if anybody wants to.